Good afternoon, everyone. My name's Andy Howard. I'm an applications engineer with Agilent Technologies, and I'm going to talk about various load pool simulation techniques within ADS. This is an outline of my talk. First, I'm going to talk about what load pool is and why do it, very briefly. Then I'll talk about working with measured load pool data and how you can use it to design impedance matching networks. And next I'll talk about simulating load pool on nonlinear device models, and this could include X parameters, and how we can do this, use this sort of simulation to determine optimal source and load impedances. Okay, first I'll talk about what load pool is and why do it. If you're designing a power amplifier, you're probably using a nonlinear device, a FET, for example. And a big part of the design process is determining what impedances to present to the output as the load and the input as the source at the fundamental second and third harmonics for the load, and also at the fundamental second and third harmonics for the source. And the performance that you get from the device really varies substantially with the load that you present to it. And by performance, I mean things like output power, intermodulation distortion, gain, power added efficiency, ACPR, air vector magnitude, things like that. Now, once you've gone through the process of determining what these optimal impedances need to be, and you've designed your input and output matching networks, you have a completed amplifier. But when you did this design, you made an assumption about what the external load impedance is. You maybe assume that it's, say, 50 ohms broadband, and maybe you assume that the source is 50 ohms broadband. Or maybe you assume that it's the input impedance of the next stage, for example. And what you can do is, a sensitivity check would be to see how the performance varies as you change the load, the external load, and that kind of indicates the sensitivity of your design to external load conditions. Okay, there are two main ways of dealing with load pool or running load pool simulations or dealing with nonlinear devices. I would say that in one case you have only measured load pool data for the device that you're using, and the other case maybe you have a nonlinear device model. Okay, the first section I will talk about is where you just have measured load pool data. This is a sample measured load pool data from Maori, and it has typically data that's a function of frequency, bias conditions, input power, and there's various data that's in the file. It could be output power, gain, power added efficiency, could be intermodulation distortion, could be ACPR, things like that. What we'd like to know is what's the optimal load to present to this device to get the best performance from it. And what we'd like to know what performance we can get from it as well. One thing that you can do if you're just given the file from somebody, say from a PA vendor or a device vendor, you can use ADS, you can use ADS, you can use this component, this database load pool component, which is new to ADS 2011, to read in the data file and look at the contours with the ADS data display. If you already know from the vendor what the optimal load is, then there's no reason to go through this. But if you want to examine the file and look at contours, you can do that. Okay, this component reads in the load pool data file, and it simulates the impedance or the reflection coefficient seen by this node, and then it gets the data that correspond to that reflection coefficient and exports that as the simulation results. And what I'm doing here is I have a load pool tuner, and we can specify some region of the Smith chart, in this case a rectangular region, and sweep out a rectangular region, present that to this component, and get the corresponding data. And typically, you'd want this tuner to specify a region of the Smith chart that corresponds to the data in the file. This is what's in the file, in the load pull file. We can see what the reflection coefficient ranges are, and we can see what the swept frequency and input power values are. And in this case, this is a very simple example where we just have a single frequency and a single input power. And then we can look at different performances from the load pull data, and these include the efficiency, the transducer power gain, and the power delivered, although you can certainly look at other data. This shows the contours from a simulation, and in red we have the efficiency, blue is the power out, and purple is the transducer power gain. This shows the contours for those three on a rectangular impedance chart, and the same data on a Smith chart. This is a more realistic example where I have a higher power device, and we have the file actually has a sweep of the available source power, and in this case it's swept from 20 to 37 dBm, and we're going to look at the load pull contours at each one of these available source powers, and in the region of reflection coefficients that are in the file. So these values for the SMAG min, SMAG max, S real min, and S real max are specified based on the data that's in the file. And because we're doing a power sweep, we can look at contours at a particular level of gain compression. This shows the contours for efficiency, gain, and output power at the 1 dB gain compression point. The red is for efficiency, blue is gain, and purple is output power. And the contours look a little bit strange because not all the data in the file is realistic. Some of it is noisy or irregular, or for certain points, certain loads, and certain input power levels, valid data was not obtained. So that's why some of the contours look a little bit strange, some of the particular points. This is a different way of looking at the data. I'm plotting on the y-axis power delivered versus power added efficiency, and we can select one of these points using this marker. In this case, we've chosen a point for higher efficiency. Again, this data is all at the 1 dB compression point. And this point that we've selected between power delivered and power added efficiency corresponds to this load in the Smith chart, or on the Smith chart. And this is a 4 ohm Smith chart. And if we choose this load and sweep the power, this red trace corresponds to the data, overall power levels. And the data in the red box over here corresponds to this particular load. This data point, which is this load. Okay, here we've chosen a load that is higher output power. Still, again, it's the 1 dB compression point. It's 1 dB compression point data. All the contours are at 1 dB gain compression, and we see a different result. You can see that the output power is higher. That's on the x-axis. So if we go back, you can see that there's a trade-off. We're at higher power but slightly lower efficiency. We can also look at the contours at a particular input power level. These are the input powers. We can select one of them that we measure or simulated, and we can plot the contours for efficiency, gain, output power, and gain compression. Okay, once we've examined the contours and we've decided what the optimal load impedances are that we want to generate, the next step in the process would be to design impedance matching networks, and you can use existing techniques, or you can actually use the measured data in an optimization. And here I'm showing a very simple impedance matching network, but we can optimize these component values across frequency, for example, and use data from the files such as efficiency, gain compression, power added, maybe distortion, just depending upon what's in here, we can use that data as part of the optimization process. Okay, and this shows the results of the optimization. Okay, and naturally the results that you actually get for your performances and for your values will depend on how you define the goals in your optimization. Okay, this is the last section, and it's on simulating load pull where you have a nonlinear device model. And this could include X parameters. Okay, if you have a nonlinear device model, you have a little bit more flexibility in what you can simulate and what you can do with load pulls. This is a sequence for running load pull simulations. You could certainly use different sequences, but this is just one that I think is a reasonable approach. But you could start off with a one-tone, one-input power load pull. This is the fastest simulation because it doesn't include any sweeps other than of the load. And then you could add a power sweep to see gain compression, which is an important specification which almost everyone is concerned about. You could add a frequency or a bias sweep and see how generally if you're designing a power amplifier across a band of frequencies, you need to consider the performance at other frequencies than just the center frequency or a single frequency, for example. And I'll show a little bit about this. The performance of your PA and of your device will vary with the reflection coefficient at the harmonic frequencies. And you can specify, we can run a harmonic load phase sweep. We can run a constant output power load pull. This is where we can do an optimization of the power delivered to the load at each, as we sweep the load, we can optimize the power delivered so that all the contours correspond to the specific power that we want delivered to the load. We can run a source pull if desired. We can do a two-tone intermodulation distortion simulation. We can also use modulated signals to see ACLR or EVM, and we can also get EVM data from one-tone swept harmonic balance power simulations. And certainly you could change this technique or change this sequence, delete steps, or iterate. This is the simplest setup. I have a tuner, or a load pull instrument, which has a tuner that allows you to sweep the load in either a circular or a rectangular region of the Smith chart, and you can specify the loads at the fundamental and harmonic frequencies to be independent of each other. And you can sweep the load at the fundamental or at one of the harmonic frequencies. Okay, from the simulation, the first simulation, we assume we fix the available source power, we guess the optimal source impedance, and we make guesses at the impedances at the harmonic frequencies, and we run a load pull we could say run a large region of the Smith chart. And what this tells us is, looking at the contours, we can see that the optimal region is over here, and we can refine the region of the Smith chart that we're simulating over. But we really don't know anything about the amount of gain compression unless we manually step the source power. And this does indicate that the gain compression is occurring. If we add a power sweep, then we can see gain compression data. This setup is the same as before, except that instead of a single available source power, we're now sweeping the available source power. And we can see gain compression data. This is, again, okay, we're looking at the performance at a single available source power, 14 dBm, and we're selecting a particular point between power delivered and power added efficiency. So we're making a trade-off between the two. Typically, you choose a point kind of along this arc, and this is the load that corresponds to this point. This data all corresponds to this point as well, and this point corresponds to this load as well. The red is the the transducer power gain and power added efficiency that you'd get if we use that load for all input powers. This is the same data, but now we're looking at performance at 20 dBm available source power, and we've chosen a slightly different load. We get better performance at higher output power, but the performance at lower output power is worse. So you can see that there's a definite trade-off in the power added efficiency here. And you're going to get different results if you match for a lower input power than if you match for, say, a higher input power. This shows the contours at 30 dBm output power. These are all interpolated data. This is a transducer power gain and gain compression. These are the power added efficiency contours. This is the same data but just on an impedance chart, and you can specify the desired output power for the contours. This shows the loads for maximum power added efficiency and minimum gain compression. So there's about 30 percentage points difference in the power added efficiency, but the output power is exactly the same, about 30 dBm. From the same simulation results, we can look at the XdB gain compression data. These are the contours at the 1 dB gain compression point for efficiency, gain, and power delivered. And this is where we've picked a load for the highest power delivered, about that point. And this is where we've picked a load for the a higher power added efficiency, we're about here. So you could choose something in between those two if you prefer. It's possible to run a frequency or a bias sweep. In this case, I'm showing contours at for power delivered at 28 dBm and at the maximum. And I did a sweep of the frequency from 750 megahertz to 1.25 gigahertz. And what this shows is that it just shows how much smaller the 28 dBm contour becomes when you go from 750 megahertz to 1.25 gigahertz. But you can see that the matching problem becomes more difficult as you go up in frequency. We can also do a load harmonic phase sweep. This is a sweep of the second harmonic phase for a high reflection coefficient. And this is a method of seeing how much the reflection coefficient, say at the second harmonic, affects the overall performance of your PA. And this shows that there is some variation. The blue is the power delivered. The red is the power added efficiency. And there's a little bit of variation. You probably want to avoid about 170 degrees or near a short for the second harmonic. Okay, just to review, I talked about basic load pool concepts and using measured load pool data files to design matching networks. And I started with a fast, simple load pool, then added sweeps to see compression and swept frequency, and showed a sweep of harmonic reflection coefficient phase. And there are certainly other techniques that I have not shown. You can run EVM analysis, for example, and you can plot EVM and ACPR from a one-tone swept harmonic balanced load pool simulation. So there are a lot of capabilities for load pool analysis, and if you have questions, please feel free to contact me or see us in the booth, and I'll give you a demonstration. Okay, thank you.